Okay, so this is Winter 23, paper 41. Let's get started. Question number 1 says, state what is indicated by the direction of the gravitational field line at a point in a gravitational field. I think this is pretty straightforward. So it just shows the direction of force, basically the gravitational force on a mass, right? So it's talking about what the field line shows, right? So it just shows the direction of force on a mass. Part 2, explain with reference to gravitational field lines why the gravitational field near the surface of the earth is approximately constant for small changes in height. So we know that in fact the field lines are radial for a mass, but if you are really close to the surface of the earth, so the field lines appear, what do you call it, parallel, because even though the earth is really big, when we are really close to the surface, so the change in height is very small compared to the size, compared to the radius of the earth. So field lines are almost parallel. So you'll say that since the change in height is negligible compared to the radius of the earth, right? This is important to say. You can't just say it's small. You say it's small when we talk about the scale of the earth. So field lines are virtually parallel. So field lines are virtually parallel. Part B, a large isolated uniform sphere has mass m, radius r. Point P lies on a straight line passing through the center of the sphere at a variable displacement x from the center, right? Then it says 1.2 shows the variation with x of the gravitational field g at a point due to this sphere for values of x for which p is inside the sphere. So this shows the gravitational field strength inside the sphere. All right, so if this is r like this, so this means this is negative r, right? So basically to the left of the origin, to this displacement from which we are measuring the reference, to the left is negative. Now to the left we see gravitational field strength is positive, and if you think about it, it makes sense, because if we are to the left, then the gravitational field strength is going to act towards the center. So in this case it would be towards the right. Yeah, so that is taken as positive. So basically just looking at this graph, I figured out that the examiner has used this sign convention that right is positive and left is negative. Does this make sense?
Yeah.
Okay. Similarly, when we are to the right, so we know that the gravitational field strength would be towards the left, so that's negative. All right, so this is given in y, where y is basically the gravitational potential, sorry, gravitational field at the surface, and r is the radius. So magnitude of the gravitational field at the surface of the sphere is y. Determine an expression for y in terms of m and r. Identify any other symbols that you use. So the expression is small g equals to capital Gm over r square. So y is basically the gravitational field strength, g, and the mass is m, the radius is r square. It says identify other symbols, so the other symbol is g, which is the gravitational constant. Pretty straightforward. All right, now in part 2 it basically asks about what we were just talking about. Explain why at the surface of the sphere g always has the opposite sign to x. So why is gravitational field strength always opposite to, however it's displaced? So we know that first of all, gravitational force is always attractive, or I can say that the gravitational field is always towards the center of the earth, right? So if you're at the right to the center, so force acts left, and vice versa. So I'll just say that since the gravitational field or the gravitational force is always attractive, you can say the force is always opposite to the direction of displacement. All right. Complete 1.2 to show the variation of g with x for values up to plus minus 3r for which p is outside. So we were drawing till r, which was from the inside till the surface of r. So I know that the expression that I also just used is this, that g is inversely proportional to r square, right? So first of all, I know that even if I go away, the gravitational field strength would have the same sign, right? If you're to the left of the sphere, so the gravitational field strength would be towards the right, and then I just need to make this according to the inverse square law. So if it's at the radius, if it's y, so when I go, when the distance away from the center doubles, this is going to fall to a quarter of its value, right? So it's going to be this. And then similarly, when the distance triples, so this would become 1 over 3 squared, so 1 over 9 of its value. And if you find this in your calculator, 1 over 9 is 0.11. So if this is 0.25 right here, so this means this is 0.05, 0.1, 0.15 and 0.2. So 0.11 is going to be just slightly ahead of this. It's really difficult to make, so almost the same. That's what I've tried to make. And then I just join this with a curve like this. All right, marking important coordinates. And then similarly in the other direction, it's going to be like this. So 2 and 0.25 and then 3 and 0.11. So that's like this. Does this make sense?
Yeah, I just have a question about part 2. Since the gravitational force is always attractive, force is always opposite to the direction of displacement. So if it's being displaced to the right, the force acts to the left.
Yeah.
How come?
Because if, let's say we're at a point like this, right? So I'm to the right, but the gravitational force would take it towards the center.
Okay. Does this have
Gravitational
anything
force
to
is
do
always
with
attractive,
Newton's
right?
third law? Yeah.
Sorry?
Does this have anything to do with Newton's third
It has
law?
nothing to do with
No.
Newton's third law.
Yeah,
It just has
okay.
to do with the fact that according to the sign convention that we also ourselves saw from the graph, if we are to go to the right, we assume a point mass, right? So all of the mass is concentrated at the center. So then the force acts towards the center of the mass, right? So this is just Newton's law of gravitation, not the
Yeah.
third law, the law of gravitation, that force is proportional to product of masses.
Yep.
So that acts towards the center. 2a defines specific heat capacity. So this is the thermal energy required per unit mass per unit temperature change or rise. Both of these are correct. An ideal gas of mass 0.35 kg. So it's an ideal gas. So I can use the stuff that are used for ideal gases, of mass 0.35 kg is heated at constant pressure. Again, something else, constant pressure, so that its internal energy increases by this much. During this process, the volume of the gas increases from this to this, and temperature increases by 56 degrees Celsius. First, it says, show that the magnitude of work done is this much. What was the equation for the work done by or on a gas at constant pressure? W equals?
nRT.
No. That's PV equals to nRT. Here the formula is this, P delta V. P is 2.0 into 10 to the 5. Change in volume is this minus this. So right now I'm not talking about whether this is work done on or by the gas. I just want to get my answer and get done with this part. So this turns out to be negative 0.025, but if I just need the magnitude, I'll drop the negative. So it's this times 2 into 10 to the 5. This turns out to be 5000 joules. Hence, I've shown that the work done is this much. Now, explain whether the work done on the gas is positive or negative. Do you know what this would be?
The volume is expanding, so the work is done by the gas.
Yeah.
And if it's by the gas, it's gonna be negative.
Yeah. Right?
Okay.
So gas is expanding, or you can say that volume is increasing. So work is done by the gas, so its energy is reducing, hence negative. Right, so now if you've done like good practice, then you already know what the next parts will be about. They will be about thermodynamics. So it says determine the magnitude of thermal energy transferred. So you know that the first law of thermodynamics is this, delta U equals to Q plus W. The previous part just told you that you should take the work done as negative 5000. You need Q because overall the internal energy is increasing by 7600. So this is also positive. So you take the 5000 to the other side, that would now be added to the 7600, and that turns out to be 12,600 joules. All right.
Yeah.
Calculate the specific heat capacity of the gas for this process. Give a unit with your answer. So now you have the thermal energy. So you can use this equation. So C equals Q over M delta T. Q is 12,600. The mass was also given. That was 0.35. And temperature increases by 56. So this is 0.35 into 56. Just looking at the units, I know that this was in joules. This is in, the mass is in kg. And with the temperature, it doesn't make a difference whether I say degree Celsius or degree Kelvin. Both of these are the same. And you just need to like evaluate this. So this turns out to be 640 joules per kg per Kelvin or joules per kg per degree Celsius. Kelvin is actually better because it's an SI unit. So let's write it like that. But it makes no difference. Now it says the gas in B is now heated at a constant volume rather than at constant pressure. So if I think about constant volume, even before reading further, this means that volume is not changing. So work done is 0, right? There's no delta V. So W is 0. Using the first law of thermodynamics, explain whether the specific heat capacity is less than, same as, or greater than your answer in B1. So this time it says that delta U equals Q plus W. Last time W was negative something, here it's just going to be 0, right? So Q this time is just going to be equal to delta U, so that's 7600. So previously Q was 12,600, now it's just 7,600. Now what this means is that less energy is required, right? Previously the energy required was 12,600, now it's 7,600. So you'll say that since less thermal energy is required for that same change in temperature, for that same mass, So specific heat capacity would be lower. Does this make sense?
Yeah.
So first I'll say that since no change in volume, work done is 0. Since, okay, so the idea is also this, that since, and this should also be like talked about because this is an ideal gas, right? So you might remember that for the ideal gas, the internal energy just depends on the temperature. So it says the increase in internal energy is the same. So since the increase in internal energy is the same, change in temperature is also the same. Does this make sense?
Yeah.
And then you say since less thermal energy is required, for the same change in temperature and obviously the same mass as well. Take this here. Specific heat capacity is lower. I'm just writing down symbols here to save time, but in your exam you should write it out fully. Moving on. 3. Product PV for an ideal gas is given by this. We know this is called the equation of state, 1 by 3 nmc square. So state the meaning of the symbols n, m, and c square. N is the number of molecules in the sample, in the gas. What's small m? Mass
Mass. Yep.
of
Mass of
it's not the total
uh,
mass, it's the mass of each molecule. All right, and c square is the mean square speed. It's not the RMS yet. When I'll take the root of this, that's when this will become RMS. Use the equation of state for an ideal gas to show that the average translational kinetic energy is given by this. This is an easy derivation. We've done this time and again. So EK is basically half mv square or half mc square, talking about one molecule, right? So I already have mc square here. So this goes there, this comes here. So you can rewrite this as this 3pv over n equals mc square, right? So this becomes half into 3pv over n, right? So then you use this equation, pv equals to n kt. So pv over n equals to kt. It must be very, very clear what substitutions you are making when. So this becomes 3 by 2 kt, right? So I use the kinetic energy equation. That's the new one. This was already given, and this is the new thing that I used. All right.
hold on. So you did
This is the kinetic energy formula, half mv square. In this case, it would be half mc square, right?
mm-hmm.
And mc square, I can make the subject from here. So that's 3pv over n. And then because of pv equals to nkt, pv over n is just equal to kt.
Okay.
Yeah. Surface of a star consists mainly of a gas that may be assumed to be ideal. Molecules of the gas have an RMS speed of this much. This is RMS, so this is with the root taken. Mass of a molecule is this much, determined to 3SF the temperature of the surface of the star. Right, so with stars, we now need to find the temperature. Okay, so with kinetic energy, I know 3 by 2 kT. So 3 by 2, I need the temperature, right? So K is the Boltzmann constant, which is 1.38 into 10 to the negative 23. And I need T, right? So this is T is equal to half mc square. So half into 3.34 into 10 to the negative 27. This is the rooted speed, so I'll have to square this. So from here you just solve, and T turns out to be 6980 Kelvin. Keep in mind that in this case, and this happens with most of the A2 questions, with most of them, that you'll have your least number of SFS3, so that's why you could not write this as 7000 Kelvin. You would lose the mark here. So with A2, it's important that you always write your answer to 3SF, because it's going to be correct in the case where it's 2SF as well. Radiant flux intensity of radiation is given, so this is basically F, right? And this is at a distance of this much from the star. Calculate luminosity, give a unit with the answer. First of all, I know luminosity is the total power of radiation emitted by a star, so it must be watts. The radiant flux intensity formula is this. I need L, so L is 4 pi d square times F, 4 pi into 4.16 into 10 to the 16 squared multiplied by 2.52 into 10 to the negative 8. All right. So when you work this out, this turns out to be 5.48 into 10 to the 26. Now to find the radius of the star, you must remember that you already found the temperature. So for this, you'll use the, what do you call it? The Stefan Boltzmann law, right? So now you have this equation that L equals to 4 pi sigma r square T4. So R is L over 4 pi sigma T4. Remember that in this case, temperature should be in Kelvin, right? With this calculation. So L is my answer to the previous part, right? So 5.48 into 10 to the 26. And obviously there's also the square root here.
Is this
Divided
formula
by,
mentioned in the formula sheets
this one is,
in the beginning?
yeah. 4 pi sigma is, hold on, what was sigma? Let me see. 5.67 into 10 to the negative 8. And T is the answer to this previous part. You should use your calculator value as far as you can. 6980 into raised to the 4. So after taking the square root, R turns out to be 5.69 into 10 to the 8 meters. So the last part of this question says the gas at the surface of a star has very high pressure. Use the basic assumptions of the kinetic theory to suggest why in practice a gas at the surface of this star is unlikely to behave as an ideal gas. So there are some assumptions, with some being tested more than the other ones. One of those which is tested a lot is this idea that the volume of the molecules is negligible compared to the volume of the gas itself. So in ideal gases, we assume that there are no forces of attraction, so particles are like very, very far apart, right? So in this case, it says if there is a very high pressure, so I would say that the molecules are very close together. So the forces between molecules that we usually assume to be negligible, the forces between molecules may not be negligible, right? Or the other one you can say is that the because there's so high pressure, so basically the volume would be less, right? So the particles would be like really close together. So the volume of the molecules, you can also say it may not be negligible compared with the volume of the gas or the volume of the container. Does this make sense?
Yeah.
Moving on. A heavy metal sphere of mass 0.81 kg suspended from a string. Sphere is undergoing small oscillations from side to side as shown in 4.1. Oscillations of the sphere may be considered to be SHM with amplitude this much, period this much. State what is meant by SHM, a very textbook definition. So motion where acceleration is, you remember this?
Where acceleration is opposite to displacement.
And proportional.
Oh
Acceleration
yeah.
is proportional to but opposite in direction to displacement. B1, calculate the angular frequency. So T is given, so I can find omega, that's 2 pi over T. So 2 pi over 3, that would be 2.1 radians per second. Total energy, so total energy formula is this, half m, it's half m omega square x naught squared, so half, and the mass was given as well, 0.81 omega from the previous part, 2.1 squared, and amplitude is 0.036 meters, so 0.036 squared. All right, this turns out to be 2.3 into 10 to the negative 3 joules. Then it says the suspended sphere is now lowered into the water. The sphere is given a sideways displacement of positive 0.36 meters from the equilibrium position and is released at time t equals to 0. Water causes the motion of the sphere to be critically damped. On 4.2, sketch the variation of displacement of the sphere from its equilibrium position with a t from 0 to 6. So initially it has a displacement of positive 0.036. So that must be here, right? And now this one basically goes to so with critical damping, the idea is that the oscillations die out very, very fast. All right. So with this, you just need to show it like this, that all right, these are your oscillations. They started and then they just die out really fast. So like, then you just continue this line. All right.
So basically, the point here starts at when they have already displaced it.
Yeah, because that's what it says in the question.
Yeah. Okay.
So that was this one. 5.8, define electric potential at a point. So work done on a unit charge and moving it from infinity to a point in the field.
Would it be fine if you said electric field?
Yeah, but you don't need to. Two isolated charged metal spheres X and Y are situated near to each other in a vacuum with their centers a distance of 24 meters apart. Point P is at a variable distance from the center of sphere X on the line joining the centers of the spheres. 5.1 shows the variation of electric potential due to the spheres at point P. Now, okay, this is a question that's not really very new to us. We know what the examiner wants us to do here. So he's just given us a very general electric potential versus distance graph, and this is between two spheres, right? So now I am supposed to make some inferences given this graph. So first of all, I can see that for one V is positive, another one V is negative. All right, so the electric potential formula is different from the gravitational potential formula because there's no plus minus here. The plus minus basically comes from the charge, right? Okay, so this distance is from the center of sphere X. So this means that X is this one, right? X is this one and Y is this one. So I can say that X is negatively charged and Y is positively charged. Yeah? So I'll say this, that X is negatively charged and Y is positively charged. Also, if I look closer, I can also figure out the radii, the radius of each sphere. Because within the sphere, I know that electric potential is going to be constant, right? So for X, its radius is 2 centimeters or 2 meters. And for Y, its radius is 4 meters. So radius of X is 2 meters and radius of Y is 4 meters, right? Apart from that, what else can I see? So I can see that the potential here at this is X, right? This is X, this is Y. So I can see that the potential here is basically it's corresponding to 4 squares. Here it's corresponding to 1.5 square. So okay, just a minute. So 2 and 20. Yeah, okay, so I can also say this. I can also say this, that the place where the electric potential becomes 0, right? This is 2, this is 20. So that's smack in the middle. When we're not inside the sphere, so this is smack in the middle. So I can also say that the magnitudes of charges on the spheres are equal. It's a bit more difficult to say, but according to the mark scheme for this is 1 mark, this is 1 mark, this is 1 mark, this is 1 mark. Obviously the max is 3, so we've already covered this. All right?
Yep.
C, a positively charged particle is placed at point P in B such that x equals to 12. The particle is released. Describe and explain the subsequent motion of the particle. So how can we comment on the motion is because I know that the gradient of this VR graph is basically electric field strength, right? And if I know electric field strength, then I know force. And then if I know what's happening to force, so by Newton's second law, I can also talk about the acceleration. This is not very difficult. So you say that for the VR graph, it's released from x equals to 12 meters, right? 12 meters. So 12 meters is here. And this was a positively charged sphere. So positively charged, I know it would be attracted towards x because that's negatively charged. right? So I'll say particle is attracted towards x, and how would I comment on what's happening? So I can see that the gradient is getting steeper down here. Gradient getting steeper means electric field strength is increasing, which causes the force to increase, which causes the acceleration to increase. So I'll say that the particle is attracted towards x and it accelerates away from y towards x with increasing acceleration. Does this make sense?
Yeah.
Also, I remember doing this question in the past with you. So I don't think this is a new one. Let's move on. 6. Define magnetic flux density. So magnetic flux density is defined by this equation, right? So you say this is the force acting per unit current per unit length. Is there something else in this equation that's not written right now? F equal to BIL. What else is there?
BAN?
No, that's a different one. That's phi. That's the equation for magnetic flux. We're talking about magnetic flux density.
Unit current per unit meter?
No, it's F equals to BIL sine theta, right? So if sine theta, if I've not written that, that means theta is 90, right?
Yeah.
So force acting per unit current per unit length for a conductor perpendicular to the field. Electrons are moving in a vacuum with speed 1.7 into 10 to the 7 meters per second. Electrons enter a uniform magnetic field of flux density this much. For 6.1 shows the path of the electrons. Whenever you have a diagram like this, you should yourself ask yourself this question that the examiner can potentially ask me, why is this moving in a circle? Right? So that's related to circular motion. In that case, you would say that this is how its velocity is, and the force is always perpendicular to the direction of velocity, right? So that's why it moves in a circle, right? I'm not sure if the examiner is going to ask this or not here. I'm just preparing myself mentally for what he could ask. Path of the electrons remain in the plane of the page. State the direction of the magnetic field. All right. So state the direction of the magnetic field given that it's deviating like this. So if it's deviating like this, if I talk about, for example, this part, then I know that force is towards the center. This is an electron, right? So if an electron is moving to the right, that means current is to the left. All right, so if I use Fleming's left hand rule, my thumb points right, my current, my second finger points to the left. All right, so do this with me. Thumb points down, second finger points like this. So it's going to be
The second
into
finger
the
points to
page.
the right, but because it's an electron, we say it points to the left.
Yeah.
Okay.
So you'd find that your index finger points into the page. Show that the magnitude of force exerted on each electron by the magnetic field is this much. So we can use this equation that we use for charged particles in magnetic fields, BQV. So B is 4.8 millitesla. It's on an electron. So charge of an electron is something you probably remember. And the speed is given as 1.7 into 10 to the 7. So all of this must boil down to this. On 6.1, draw an arrow to indicate the direction of the centripetal acceleration of the electron where it enters the magnetic field at point X. So I know that the centripetal acceleration is towards the center. This is how the arrow would look like. Next, use the information in B2 to calculate the distance d between the path of the electrons entering the magnetic field and the path of the electrons leaving it. So I can see that d is basically twice of the radius. So this d, which is what the examiner is calling the distance, that's also the diameter, right? So now I need the diameter. So I'll use this equation. I know that in this case that the magnetic force provides the centripetal force for the electrons to move in the circular path. So I say that BQV equals mv square over r. V's cancel out like this. I need r, so that is mv over bq. And I know that if I need d, that's going to be twice of this. So d is basically 2mv over bq. 2 mass of an electron is 9.11 into 10 to the negative 31. V is 1.7 into 10 to the 7. B is 4.8 millitesla. And Q is 1.60 into 10 to the negative 19. Right? So I just plug all of this into the formula. Let's do this.
You just changed the letter here from R to D, right? You didn't multiply by 2 or anything.
Sorry?
The letter R to D, the change in that, you didn't change anything with it, right? Value.
I just use this idea that R is this much. This is R. And then this is also R. So D would be like 2R.
Yeah.
Yeah, that's
So
it.
did you multiply by, or did you divide by, or multiply, did you multiply by 2 or something when you changed it to
Yeah,
D?
there wasn't a 2 here. And now there's a 2 here.
Oh, right. Okay.
Yeah. All right. Electrons in B are now replaced with positrons that are moving with speed 3.4 into 10 to the 7. So the speed has basically doubled, right? Speed has doubled. Along the same initial path as the electrons, positrons enter the magnetic field at point X. Draw a line to show the path of the positron. So I can see that if V doubles, then the radius of curvature would also double, right? And if the electrons were moving downwards, then the positrons will move the other way around. All right. So now this is just going to become something like this. Larger radius. But larger, like this. So like this, but in this direction. Let's go on. 7. A varying current I passes through a resistor of resistance R in the circuit as shown in 7.1. So you have I, which is basically a square wave. All right. Current has magnitude 2 I naught when it's in the opposite direction and I naught when it's the negative direction. And I can also see that it's the equal amount of time for when it's positive and when it's negative, right? With this being one time period, right? After this being one time period like this. And then it repeats. Determine expressions in terms of I naught and R for the power dissipated when the current is in the negative direction, when the current is in the opposite direction. So first of all, I know that it won't make any change to the current if I also remember the expression P equals to I square R, right? So with current in the negative direction, it's just going to be minus I naught square R, but the square of a negative number is also positive. So this is I naught square R. In the positive region, it's going to be 2 I naught square R. So the square of 2 I naught would become 4 I naught square multiplied by R. Yeah?
Yeah.
Then it says on 7.3, sketch the variation of P with T between from 0 and 2T. Label the power axis with an appropriate scale. So it's going as high as 4 I naught square R, right? So I now need to make a scale. So it's going as high as 4 I naught square R. So let me call this 4 I naught square R. This would then be 2 I naught square R, right? And then this would be 3, and then this would be 1. So from 0 to 0.5, it's going to be I naught squared R. So I naught squared R is going to look like this. And then it's going to instantaneously jump to 4 I naught squared R. So that's going to be like this. And then I naught square R, and then 4 I naught square R, and then I just join all of these. Yeah?
Yep.
Use the expression in B to determine an expression in terms of I and R for the mean power in the resistor. Now, in this case, I can see that equal times it's this, and then other times it's this, right? So if you remember the examples we did, we also did cases where the time period was unequal. But here I don't have to do that because they are there for like equal time, so I can just average. So 4 I naught square R plus I naught square R, and then I half this. So that just turns out to be 2.5 I naught squared R, right? So basically 4 plus 1 over 2, and you have I naught square R, right? 4 I naught square R plus I naught square R divided by 2. That's what this is. The RMS. So now you need to recall what the RMS really means. So you say that the RMS causes the same power dissipation. So the RMS is that value of the DC current which causes the same power dissipation as the AC current. So you'll say that 2.5 I naught square R is basically equal to I RMS squared R. So R's cancel out, and I RMS is basically root 2.5, right? So this becomes root 2.5 of this, and you'll also have I naught. So root 2.5 is 1.58 I naught. Yeah? This is what
Yeah.
we've done.
What means squared? Did we do like from end to beginning, like square and then the mean and then the root, or
Sorry, I don't understand what you're saying. Let's go on. 8. Show that the momentum of a photon is given by this expression where h is the Planck constant. We've done this as well. So P is given by E over C, and if you use, instead of E, if you use hc over lambda, because E equals hf, so you can write that as hc over lambda. So this becomes hc over lambda over C, so C's cancel out, and this is just P given as h over lambda. Use the expression in A1 to show that a photon in free space has a momentum that has a momentum of this much is a photon of red light. So red light is basically the longest wavelength, 700 nanometers. This is what we did in AS waves. So we need to find the wavelength. H is a Planck constant, so that is 6.63 into 10 to the negative 34. And P is 9.5 into 10 to the negative 28. And this, if you work this out, will actually turn out to be 700 nanometers, and hence this is red light. All right, so the other end is violet light, which is the shortest wavelength. That's 400 nanometers. A beam of red light of this intensity is incident normally on a plane mirror. Momentum of each photon is given. All of the light is reflected by the mirror in the opposite direction to the original path. Cross-sectional area of the beam is given. Right, so intensity is given, area is given, so I can find the power of the photons. Right, but let's see what the question is asking for. So it says that show that the number of photons incident is this much. Now I know, again, this is exactly what I'll have to do, since intensity is power over area, power is intensity times area. So intensity is 160 watts per meter square, area is this much. So 160 into 2.5 into 10 to the negative 6. This is the power of all the photons, right? So this turns out to be, let's work out this. This is 4 into 10 to the negative 4 watts, which is basically 4 into 10 to the negative 4 joules per second. So if I know that this beam, which is incident, has a okay, so I know, just a minute, I know the momentum, right? So then can I find out its energy? And the answer is yes. Right, so 9.5 into 10 to the negative 28. So I already know the wavelength for that. Right? So momentum, so this is power, and then I just do this, that just a minute. Oh yeah, so we need energy, right? So I have P and I have C, so I can just find energy as PC, right? That would be the energy of one photon. So energy of one photon is PC, which is momentum 9.5 into 10 to the negative 28 times 3 into 10 to the 8. Right, this is the energy of one photon, and power is basically the power of all the photons, right, which is the energy per second of all the photons. So 9.5 into 10 to the negative 28 into 3 into 10 to the power of 8. This is 2.85 into 10 to the negative 19 joules, right? So if I just divide this by this, so power of all the photons, or I can say the energy of all the photons per second divided by the energy of one photon. So if I just do this over 2.85 into 10 to the negative 19, so I get the number of photons, 4 into 10 to the negative 4, 2.85 10 to the negative 19, that is 1.4 into 10 to the 15. So this is what you get. Use the information in B1 to determine the pressure exerted by the light beam on the mirror, right? So pressure is force over area. But again, the problem is this, that how do I find the force in this case? So the force I can find by the rate of change of momentum. And I know that because this is rebounding, all of the light is reflected. So there is basically the change in momentum would be equal to twice the initial momentum, right? So it has this momentum, let me call this P going in, and then it also has P going out. So if I do delta P, which is PF minus PI, and if I use my sign convention, let's say right is positive, left is negative. So the left one would be minus P, the initial, and the final one would be minus P, and then minus the initial, which is just positive P. So this becomes 2P if I'm just looking at the magnitude. So delta P over delta t, which becomes with this thing a delta t. So delta p would be twice 9.5 into 10 to the negative 28. All right. And okay, so this is basically happening in, so this is the number of photons incident in 1 second, right? So if I have this happening in 1 second, so I can just multiply by this to get the total pressure exerted, right? Because what we are doing, the change in momentum, this is for 1 photon, right? Now I would divide by the time. So let's say this is for 1 second. So in 1 second, you have a total of this many photons being incident here. And then A, the area, which is given as 2.5 into 10 to the negative 6. So you multiply this and the pressure turns out to be 1.1 into 10 to the negative 6 pascals. Beam of red light is now replaced with a beam of blue light of the same intensity. Suggest and explain whether the pressure exerted on the mirror by the beam of blue light is less, same, or greater than the pressure exerted by the beam of red light. So I know red light has the largest wavelength. So in going to blue, first of all, I would say that wavelength decreases. Now if wavelength decreases, so it's the same intensity, right? So for that same intensity, if wavelength decreases, how would this affect the energy, right? So if wavelength decreases, I would say energy increases, right? So energy increases, that causes the momentum to also increase. If I look at both of these together, this goes down, this goes up, momentum goes up. So momentum of the photons goes up, and if momentum of the photons go up, so you will have more energy. But you can see that if you have more energy per photons, then for the same intensity, there are now going to be less photons coming in, right? So if you think about this, you will have a greater change in momentum, but then this thing, the number of photons which you actually calculated using this, right? So energy would go down. So energy goes down, which is this thing, right? And intensity stays the same. So the number of photons go up. But if the number of photons do go up, then this is basically an inverse proportion. So then their product would still be the same. Their product is still the same. This is a bit dense to grasp at first impressions. But if you like calculate this, you'll probably have like more belief on why or how this is. So you say this, that the photons have greater momentum and energy but since intensity is constant, less number of photons are incident, so pressure remains constant. You can probably also just see it using this here. If you think about it, this is 4 into 10 to the negative 4, which was what? Yeah, so this was intensity times area, right? So that's the numerator in this case. The denominator here is this into this, right? So just for a minute, if I erase this and write it out fully, So this would be 9.5 into 10 to the negative 28 into 3 into 10 to the 8. This turned out to be 1.4 into 10 to the 15. Right? Now 9.5 into 10 to the 28, this is basically energy. This is C. And this is the number of photons incident. Right? So if I do this, that if the wavelength goes down, momentum increases, causing the energy to increase. So energy increases here, right? But if the energy increases, this is definitely going to decrease, because this is a constant. Because this is the product of intensity and area, this is a constant. This is the speed of light, this is a constant. So I can say that E, the energy, and N, the number of photons, these are basically inversely proportional. If E goes up, then N goes down. So that's why it's like this. Okay, next part, next question. How many more do we have? 9, 10. Okay, second last. State what is meant by nuclear fusion. So you say two unstable lighter nuclei join to form a larger stable nucleus. So ingredients, the reactants are many, but the product is one. Sketch the variation of binding energy per nucleon with nucleon number for values between 1 and 250. So this is how it's supposed to be, with this peak occurring at iron, which is 56. This is important to label. On your line in 9.1, label a point X that could represent a nucleus that undergoes alpha decay and a point Y that undergoes nuclear fission, right? Okay, so for something that undergoes alpha decay, this is going to be something like this, because there is the heavier nuclei that undergo alpha decay. So this is probably here. And a point that undergoes nuclear fusion, these are the lighter elements that fuse together to have a greater binding energy per nucleon number. A nucleus Z undergoes nuclear fission to form strontium and xenon. According to this equation, 9.1 shows the binding energies of strontium and xenon. Fission of 1 mole of this releases 1.77 into 10 to the 13 joules of energy. Determine the binding energy per nucleon number in mega electron volt of Z. Okay, so this is the fission of 1 mole of Z, right? So first of all, I can figure out what Z is, what the nucleon number of Z is. So the nucleon number is going to be 93 plus 139 plus twice of this, but there's also a 1 neutron here. So it's going to be 1 less than that. So nucleon number of Z is going to be 93 plus 139 plus 2 times 1 and minus 1, right? So 93 plus 139 plus 1, that is 233, is the nucleon number of Z. I need this because I'll need to do mole calculations later. So the fission of 1 mole of Z releases this much. Binding energy per nucleon number is what I need, per nucleon number, right? Okay, so can I somehow find the, what do you call it? Can I somehow find the energy released per nucleus? Because if I have per nucleus, then I can divide by nucleon number to get the binding energy per nucleon. This is of 1 mole. I know 1 mole contains 6.02 into 10 to the 23 particles. So first I'm finding the binding energy per nucleus. Then I'll divide this by the number of nucleons. So 1.77 into 10 to the 13 is for 1 mole. 1 mole contains 6.02 into 10 to the 23. So first I figured this out. So 1.77 into 10 to the 13 or 6.02 into 10 to the 23, just 2.94 into 10 to the negative 11. Now for the actual binding energy calculations. So you have strontium and xenon which are forming, right? So this is the binding energy per nucleon of, this is the binding energy per nucleus of Z, right? So yeah, so this is basically the binding energy. Let me just remove this word. Might just make this more confusing. This is just the binding energy of Z, right? So if I just do this, that the binding energy of Z is this much, I have the binding energies of the product. So I can just add the product, subtract this to get the, no, wait a minute, what am I saying? Just a second. Okay, this is not the binding energy at all, my bad. This is the energy from one nucleus of Z, right? So the nucleus, from one nucleus of Z, this gives you this energy in joules, right? So this gives you this energy, and then these have this binding energy. So by subtraction, I can figure out the binding energy of Z now. So if I do 1.25 plus 1.81, that's obviously larger than this. So I'll do 1.25 plus 1.81 into 10 to the negative 10 minus 2.94 into 10 to the negative 11. So 1.25 plus 1.81 10 to the negative 10 minus 2.94 into 10 to the negative 11, that is 2.766 into 10 to the negative 10 joules. Now this is the binding energy of Z, right? And now I'll just divide this by the nucleon number. So just divide this by 233, but this is in mega electron volts, right? So I would just do this thing, divided by 233, and then to convert this to mega electron volt. So 1 electron volt is 1.60 into 10 to the negative 19 mega electron volt. So there's also a 10 to the negative 13 additionally. So this would turn out to be 7.43 mega electron volt, and that's how this calculation goes. Last one is on medical. Ultrasound and X-rays are both types of wave that are used in medical diagnosis to form images of internal body structures. Complete 10.1 to state for each type of wave the method of production and whether the wave that is detected and used to form the image is the wave that has been absorbed, reflected, or transmitted. So for ultrasound, it's the one which is reflected, right? So the wave that is reflected and is detected back by the probe is what is used to construct the image for ultrasound. For X-ray, it's the one which has been transmitted, the one which goes through, right? That is what causes the blackening on the screen. Method of production for ultrasound is the vibration